prior to 1897, lots of ideas about the atom. The predominant theory is the Dalton solid sphere model of the atom, which says basically that the atom consists of a single solid sphere. Now, each atom is different. An atom of this might be different than an atom of that, but there's nothing smaller than the atom itself. It's a solid sphere. It's like a marble. You got a marble, and this marble may be different than that marble, but in the end, the marble is as small as it gets. So we enter J.J. Thomson in 1897, and those of you taking chemistry are going to know who J.J. Thomson is. He's the guy who discovered the electron. He's the guy that came up with the plum pudding model of the atom, which says that the atom consists of a sea of positive charge with a whole bunch of little negative electrons floating around inside. Prior to him, there was no evidence whatsoever to suggest that there was anything smaller than the atom. In 1897, J.J. Thomson discovered the atom by using something that we call a cathode ray tube. And the cathode ray tube is the basic component behind the older style televisions. The TV that's in the corner of the room right now. Not the one that you're looking at right now. Okay, that's an LCD projection unit. The TV that you're looking at in the corner of the room right now is based on a cathode ray tube. The big, heavy, thick, deep TVs are based on these cathode ray tubes. That's what Thomson used to discover the electron. Now, I'm going to draw a better picture than that, actually. I don't like that picture. What does the cathode ray tube consist of? Well, in its most basic form, it consists of an evacuated glass tube. What does that mean, evacuated? Yep. Yeah, inside of it is a vacuum. Everything's sucked out of it. Okay, there's no air inside of it. There's no anything else inside of this glass tube. So it's just empty space. But we have attached to one end an electrode, and somewhere closer to the middle we have another electrode with a little bit of a hole inside it. Now, tell me which one's going to be negative, which one's going to be positive. Yep. Good. The one on the left side is going to be negative, and the one on the right side is going to be positive. This negative terminal, this is going to confuse you a little bit if you've taken chemistry. This negative terminal we're going to call the cathode. And the positive terminal we're going to call the anode. Now, Thompson used this cathode ray tube in 1897. Cathode ray tube was invented, I should say, not discovered, invented maybe 50 years before that, sometime in the late 40s or 50s. But it was kind of perfected over the years as we reached the year 1897 and Thomson was going to use it. In its most basic form, it consists of this: 2 electrodes, an evacuated glass tube. And prior to Thomson, lots of people noticed when you flip the switch to turn this thing on, there was this kind of greenish glowing something leaving the cathode going toward the anode. Now, this anode has a hole in it, so whatever this greenish glow ends up going right through it and striking the screen over here at the end. This part, by the way, would be your TV screen if you were looking at the cathode ray tube in a TV. So this mysterious greenish glow is leaving the cathode, going toward the anode, going through a hole in the anode, and then going straight to the screen and hitting the screen. Lots of people over 30, 40, 50 years had ideas as to what this was. Some people said maybe it's some kind of electromagnetic radiation, some kind of light. Maybe some people even said some kind of particle, charged particle, but nobody really knew what it was. Thomson, in 1897, introduced a magnetic field down here. This is a big deal, because when he introduces this magnetic field, all of a sudden, this mysterious greenish glowing, we called it a cathode ray because it left the cathode, go toward the anode. It changed direction, it went like this. What did that tell Thomson? Well, there's only one thing that one general category of things that this mysterious greenish glowing thing could be if it was deflected downward in a magnetic field. It's got to be a negative particle. only negative particles are deflected downward in a magnetic field pointing into the page. Now, some of you are thinking, well, how do we know that it's a negative particle? How do we know that negative particles react a certain way to magnetic fields when we didn't even know about the existence of the electron? We knew about negative charge. We knew about positive charge. Remember, I think it was 1819 that Ørsted made his discovery. I think it was 1819 that Ørsted made his discovery that moving charges generate magnetic fields. We knew about charge. We just didn't know where charge came from. We didn't know that it came from subatomic particles. Okay, we knew about negative charge. Negative charge here is deflected in a certain direction in a magnetic field. Therefore, this mysterious greenish glow must be negatively charged particles. Now, how do we know exactly where it hit the screen? Well, because this screen is painted. It's painted with, called a phosphorescent coating. Okay, look at the TV up there right now in the corner. It's black, right? Why is it black? Because it's painted. The inside of the glass is painted with a phosphorescent coating. It glows. This paint is a special paint that glows when electrons strike it. So Thomson's got this mysterious greenish glow called cathode rays that are going from the cathode toward the anode, through this magnetic field that's deflecting them downward. Therefore, he concludes that they're negatively charged particles. They're striking the screen, causing the screen to glow right here, or wherever they strike. So he knows they're negatively charged particles, but he doesn't know yet that they're subatomic negatively charged particles. People have discovered negatively charged particles. Okay, he hasn't established anything more than these are the negatively charged particles that other people had already discovered. So he says, you know what? I want to know something about these negatively charged particles, not just that they're negatively charged particles. I want to find out something about them. I want to measure some of the properties. So he looks at it and says, oh, wait, I did this in my physics 30 class. I know that negatively charged particles going through a magnetic field go in a circle. Therefore, we can analyze the path of these mysterious negatively charged cathode rays by saying Fc is equal to Fm. That's what we did earlier in physics 30, right? So Thompson did. Said mv squared over r equals qvb. One of the v's cancels, and we're left with mv over r equals q times v. Perfect. Let's plug in some numbers. Let's solve for something. Let's measure some property of these negatively charged particles that we didn't have before. B, the magnetic field, good to go. He put the magnetic field in there, so he's got to know the value of the magnetic field. R, what's the value of R? Well, he looked at where they struck the screen and then measured R from where they struck the screen. So that's a relatively easy one to find as well. M, don't know M. Don't know what the mass of these particles are. Okay, that's okay. V, don't know how fast these particles are moving. B, Q, don't know what Q is either. Don't know what the charge is. So basically, he came up with an equation to try to establish some of the properties of these mysterious particles, but yet that equation had 3 unknowns in it. So it really wasn't very helpful. We're going to add one more section to this cathode ray tube now. The other section is going to have a magnetic field as well. That's going to cause a magnetic force on these negatively charged particles, a downward magnetic force on these negatively charged particles. But in the same place, he's going to introduce, let's make a new color here. Let's go with this one. If I can get rid of that one. He's going to introduce 2 charged parallel plates, top one positive, bottom one negative. That causes an electric force upwards. Now, some of these negatively charged particles are going to be going too fast or too slow. And if that's the case, then these negatively charged particles will be either deflected upwards or downwards. In other words, if the electric force upwards is bigger, they're going to be deflected upwards. If the magnetic force downwards is bigger than the electric force, then they're going to be deflected downward. So if they're moving too fast or moving too slow, then they're going to be deflected upwards or downwards. But for the particles that are going just the right speed, and only one particular speed, we'll do this. For the particles that are going just the right speed, we can say that the upward electric force is equal to the downward magnetic force. Only for certain particles. Most of them, that's not going to be the case. But for certain particles that are going just the right speed, not too fast, not too slow, those two forces will balance. The electric force is QV, the magnetic force is QVB. Q's cancel, and lo and behold, the speed of these particles is the electric field over the magnetic field. Now, he measures the value of the electric field. He put it in there. He knows what its value is. The magnetic field, same deal. He knows what it is. So now he can calculate the speed of these particles. Not all of them, because some of them were deflected upwards and some were deflected downwards. But he knows the speed of the particles that went straight through. And those are the ones that we care about, because those are the ones that enter this last section over here where Fc equals Fm. This last section that I like to call the main chamber. That's not an official name for it, but that's what I like to call it. The particles that go straight through enter the main chamber. So that's good, because when we know the value of V, the speed of the particles that go through into the main chamber, we now have one more given. That's a big deal. It might not seem like it because we still have two unknowns. But to go from 3 unknowns to 2 unknowns is a big deal. Because although we can't solve for either of the unknowns, Q or M, and boy, would we ever like to. Okay, we want to measure some of the properties of these charged particles. Charge and mass are probably the two big properties we want to measure, right? But we can't. Because we don't know charge, we don't know mass. But what we can do is find a ratio between them, which is better than nothing. Someone knocks at the door and says, Rucker, how old are you? And Rucker says, I don't want to tell you. Then he says, Mr. Dickie, how old are you? And I say, I don't want to tell you. And then somebody says, and then the guy at the door says, well, at least tell me the ratio of your ages. And I say, okay, the ratio of my age to Rucker's age is 2 to 1. Well, the guy wanted to know Rucker's age. He didn't find it out. He wanted to know my age. He didn't find it out. But at least he knew the ratio when he walked away. It's not what he wanted to learn. It's not what he wanted to know when he walked away. But it's more than what he knew when he came in. The ratio of my age to Rucker's age. So what we're going to do here, what Thompson did, is couldn't find the charge, couldn't find the mass, but he could find the ratio of the charge to mass. And you guys learned earlier in Physics 30, when you want to find a ratio, what's the word? The D word. You divide. So let's divide Q over M. Let's take the M over by dividing. So this M goes over by dividing. And then let's take the B over to the other side by dividing. So we don't know Q, we don't know M, but because we know the value of V, B, and R, we do know the charge to mass ratio. Now, the charge to mass ratio for an electron, or for these cathode rays, these mysterious negatively charged cathode rays, worked out to be, I believe it was, don't quote me on this number, we'll check it a little bit later on, I believe it was 1.76 times 10 to the 11 coulombs per kilogram. Now the number, not the exact value, but the magnitude of that number has some pretty big significance here. That's a big, big charge to mass ratio. We knew about charge prior to Thompson. We knew about mass prior to Thompson. We had found the charge to mass ratio of particles, of things, of atoms prior to Thompson. But nothing was this big. This was by far the biggest charge to mass ratio ever measured. Why is that a big deal? Because if it's the biggest charge to mass ratio ever measured, if you got a really, really big number right there, what does that tell you about M? What does it tell you about mass? It's really, really small. In fact, if it's the biggest charge to mass ratio ever measured, it's the smallest mass ever measured. So if it's smaller than the mass of an atom, then what do we know about these negatively charged particles if it's smaller than the mass of an atom? They got to be smaller than atoms. So now we've established that they're not just negatively charged particles, but they're negatively charged subatomic particles, right? And what's a negatively charged subatomic particle? What do we know it to be now? An electron. There's the discovery of the electron. This is the first evidence of subatomic particles, particles that are smaller than the atom. Does that make sense? Now, how's the analysis there? The math make sense there? Okay, good. There is one more little bit of math that we rarely have to use. I'm going to just briefly say something about it. We've already talked about it back in Unit 2, in fact, and we addressed it a little bit in our last unit as well. Way over here, we haven't paid much attention to that. Way over here, these charged particles are accelerating from rest to a certain speed right there. When we have charged particles accelerating, then we say EI is equal to EF, or QV is equal to 1/2 mv squared. So why is it that we needed to put this second chamber, this second section in here, which, by the way, we call the velocity selection chamber? Why do we need to introduce that? Look, we needed to find the speed for the main chamber. Couldn't we have gotten the speed right here? Just put it into the main chamber? Yeah, we could have. The only problem with this is that this assumes 100% efficient energy conversion. That's the maximum possible speed. It's kind of like in the photoelectric effect, remember? We didn't know exactly how fast the electrons are moving when they left the atom. We found a maximum possible speed. Same kind of deal here. We don't know exactly how fast they're moving when they reach the anode. This is the maximum possible speed they can be moving when they reach the anode. So, hey, that number is better than nothing, the F right here, but this is a much better way to find speed because this is maximum possible. This is the exact speed those particles are moving as they enter the main chamber. So, just a couple of words about that of explanation here. It says, Thomson measured the charge to mass ratio of the electron, Q over M, right? Did that mathematical analysis that we just did. It was really, really big. Since it was really, really big, in fact, bigger than anything else ever measured, than any other known charge to mass ratio, he concluded that these were really, really small particles. Really big charge to mass ratio. Therefore, really, really, really small mass. And if they were small mass, smaller than any other mass ever measured, then they had to be subatomic particles, fundamental subatomic particles. Ironically, this was the first of the subatomic particles discovered. Electrons, and then later on came, what came after electrons? Protons and neutrons. Electrons were the first ones discovered. They're still now of the original 3 fundamental particles, they're now the only fundamental particle we have. Protons and neutrons, we now know can be broken down into smaller things. But still, the first one ever discovered, electrons, we still think, we're pretty sure about this, that they can't be broken down any further, that they're as small as they can be. We're going to do a quick little problem here that involves this cathode ray tube that Thomson used to discover the electron. It says, a beam of electrons passes undeflected through a 0.5 Tesla magnetic field combined with a 50 kilonewton per Coulomb electric field. I don't like this kilonewtons per coulomb thing. The electric field, the magnetic field, and the velocity of the particles are all perpendicular to each other. Man, this word perpendicular keeps arising, right? That's pretty much every time we talk about a magnetic field, the word perpendicular comes up. How fast are the electrons traveling? This is a cathode ray tube problem. Let's go back to this diagram, though. Which section of the cathode ray tube is it? Is it the acceleration chamber? Is it the velocity selection chamber? Or is it the main chamber? Let's look at what we have again. We've got a magnetic field. We've got an electric field. We've got the particles going undeflected. Okay, that's a key word right there. Undeflected through the electric and magnetic field perpendicular to them. We want to know the speed of the particles. Which chamber are we dealing with there? Acceleration, velocity selection chamber, or main chamber? Yep. Good, it's the velocity selection chamber. Okay, two things that tell me that. One, whenever I see the word undeflected in the context of the cathode ray tube, it's probably going to be the second section, the velocity selection chamber. And secondly, whenever I see an electric field and a magnetic field at the same time, then I'm probably going to make it a velocity selection chamber problem. So let's go Fe equals Fm. You don't necessarily need to derive it every single time, but I think you should. I think you should because the equation that we have for the velocity selection chamber, V equals E over B, that's not on our data sheet. But Fe is on your data sheet, and so is Fm. Cancel those out, ends up being V is equal to E over B. So we're just going to divide those two numbers now. We get E is 50,000 newtons per coulomb, and B is 0.50 Tesla. Do the math there. Should work out to be 1.0 times 10 to the 5, I believe. Somebody double check that. Let's assume that it is 10 to the 5 for a second. Is that a reasonable speed? What do we usually get for the speed of a charged particle? 10 to the 5, 10 to the 6, maybe 10 to the 7. That's a reasonable speed. I think it's right there. Just double check that to make sure. All right, guys, have a look at page 756, number 1 of 3 then. Remember, when you're solving these problems, assuming it's a cathode ray tube problem, which, of course, these three are all going to be cathode ray tube problems. For these problems, you've got to identify not only that it's this general concept of a cathode ray tube, but what part of the cathode ray tube is it? Is it the acceleration chamber where EI equals EF? Is it the main chamber, the velocity selection chamber where Fe equals Fm? Or is it the main chamber where Fc equals Fm? Okay, figure out which section it is and then do your thing. So it's kind of like, yeah, it's a cathode ray tube problem, but specifically, what kind of problem is it? And that's what you got to figure out when you solve these problems. Okay. Okay, let's take a look at question number 2 here. What magnitude of the electric field will keep protons from being deflected when they move at a speed of 1.0 times 10 to the 5 through this magnetic field? Protons? That's not a cathode ray tube. Cathode ray tube are electrons. You know what, guys? Sometimes we deal with problems that are like cathode ray tubes, but they're not cathode ray tubes. Sometimes we're dealing with something like a mass spectrometer, which is exactly the same as a cathode ray tube, except a mass spectrometer uses ions. Sometimes we ionize atoms, run them through this mass spectrometer in order to determine some of the properties of these ions so that we can determine what the unknown atom was, what the composition of it was. Okay, but in the end, acceleration chamber, velocity selection chamber, main chamber, same thing, whether we're dealing with technically a cathode ray tube with a negatively charged electron or proton or any other kind of ion. So that's kind of where we are in this question. We've got a velocity selection chamber. We've got a speed. We've got a magnetic field. And we're looking for an electric field. So we're going to say once again, even though it's not technically a cathode ray tube question, we're going to say it's a velocity selection chamber question where Fe is equal to Fm, Qe is equal to QVB, Q's cancel, V is equal to E over B. Well, in this case, actually, we don't even want to rearrange that, right? Just say E is equal to V times B. So it's going to be 1.0 times 10 to the 5 meters per second times magnetic field of 0.05 Tesla, which when we multiply these two together, what are we going to get? What are we going to get here? 5.0 times 10 to the, is that 3? 5.0 times 10 to the 3? Hey, I'm curious what they put for the answer, actually. Oh, they did it right. Why do they say one digit there? Should be one digit. Because this is one digit, right? 0.05 is a one digit. Okay, good news is on an exam, they always tell us, right? Round and record your answer to 3 digits. Round and record your answer to 2 digits or 1 digit or whatever the case may be. Probably not going to be a 1-digit answer on your exam, because then you got a 1 in 10 chance of getting it right, of guessing it, right? Probably going to be a little bit, at least 2 digits, right? All right, question number 3. What magnitude of magnetic field will stop ions from being deflected when they move at a speed of 75 kilometers per second to an electric field of this value? Stop them from being deflected. Okay, don't think, oh, stopping potential or something like that. This is not a photoelectric effect question. Stop them from being deflected means undeflected. It means, once again, the velocity selection chamber. And we're talking about ions. So again, technically not a cathode ray tube. It's a mass spectrometer probably. But same thing, right? Same thing except not electrons. We're going to say Fe equals Fm. We're going to say QVB, Q times E, electric force equals QVB magnetic force. And we're going to say V is equal to E over B. E is, no, wait. We're looking for magnetic field, right? So we're going to rearrange that to solve for B. It's going to be B is equal to E over V. So E was 150 newtons per coulomb, and V was 75 times 10 to the 3 meters per second. We do that math, and it works out to be 2.0 times 10 to the negative 3 Tesla. Is that okay? I can't remember who asked me for question 2 and 3, but is it good? You asked me for one of them. Sorry? Did you ask for one? Oh, well, let's do question number 1 then. Well, I wish I had listened more carefully and heard that. Let's take a look at number 1 then. A beam of electrons passes undeflected. Undeflected, again, it's the velocity selection chamber. And this is a beam of electrons, so it is a cathode ray tube problem. This magnetic field, this electric field, what's the speed of the particles? Fe equals Fm. Qe equals QVB, like it is whenever we're dealing with the velocity selection chamber. V is equal to E over B. The speed is equal to electric field divided by magnetic field. So it's 60,000 newtons per coulomb divided by 2.50 Tesla. I would do that math, and it should work out to be, I think, 2.4 times 10 to the 4. Is that okay? Any issues with those? Good? Okay, let's do one more example, then we'll call it a day here. 758 or 15.2 on 758. When a beam of electrons accelerated to this speed is directed perpendicular to a magnetic field of this value, they travel on a circular path with a radius 3.37 centimeters. What's the charge to mass ratio? What's the charge to mass ratio for this electron? So until we see that word charge to mass ratio, or that term charge to mass ratio, we look at this as, you know, just any other magnetic field question that we did back in our magnetism unit, right? But when we see charge to mass ratio, we're thinking, oh, okay, this is the main chamber of a cathode ray tube. Main chamber being that last chamber where Fc equals Fm. mv squared over r equals qvb. Right, we know this because it's going in a circle. We know this because there's just a magnetic field. One of the v's cancels. I get mv over r equals q times b. And I got to rearrange the solve for q over m. So let's take the m down by dividing. Let's take the b down by dividing. It becomes q over m equals v over b times r. The speed is 5.93 times 10 to the 5, divided by b, which is 100 times 10 to the minus 6 Tesla, times 0.0337 meters. Let's do this on the calculator. Let's say 5.93 times 10 to the 5 divided by, let's use some brackets here, 100 times 10 to the minus 6 times 0.0337. 1.76 times 10 to the 11, which is the same number as I gave you when we did the lecture on cathode ray tube, right? This is what Thompson found the charge to mass ratio to be. It was such a big number that it had to be a subatomic particle. 1.76 times 10 to the 11 coulombs per kilogram. Listen, if you got the value of Q and M already, just divide those two numbers. But if you don't, then you can always find the charge to mass ratio by V over BR. And in this question, they want us to assume that we don't have Q and M already. Okay, is that okay? Okay, let's take a look at those three questions now to go along with that, please. Again, same deal as last time, right? Cathode ray tube problems, right? But try to make sure that you understand why it's a cathode ray tube problem or something like a cathode ray tube, and then which section of the cathode ray tube is it? Is it the acceleration chamber? Is it the velocity selection chamber? Or is it the main chamber? Is it EI equals EF? Is it FE equals FM? Or is it FC equals FM? And understand why you picked what you picked. If you finish these questions up in the next minute or so, then I'd like you to take a look at worksheet number 22 as well. And homework for tomorrow on worksheet number 22 is going to be the odds. There's 10 questions. I don't want to give you 10 of those questions for homework, but 5 of them I think is fair enough. So finish these 3 questions up if you haven't already, and then do the odds 1, 3, 5, 7, and 9 on worksheet number 22, please, for homework tomorrow.